Hello everyone, I welcome you all to Startup Academy, India's exclusive coaching for ISS examination. In today's lecture, we will be dealing with a new topic which is weak law of large numbers. Now, weak law of large numbers can also be denoted as WLLN. I'm writing it in short form, it is WLLN. So, where does this concept of weak law of large number came? Suppose I am having a coin, an unbiased coin, which has a one, which whose one side is head and the other side is tail. Now, if I toss the coin, I'll be getting either head or tail. And when I keep on tossing the coin up till n number of times, and this n number of times is infinity, so I am having a large number of tosses or the experiment outcomes that we have. So the large number comes from this concept. Then when we have n number of experiments of the same thing, then we call it large numbers. And weak because it gives us the probability that it converges, that xn is a sequence of random variable, converges into some value x with probability or in probability. It does not converge into almost surely, or it does not give the surety that it will converge into that only. It is just a probability. That's where we came from. So when I am tossing the coin head, then this sequence of random variable where we are getting head is denoted by xn. So these are the sequence of random variables that we are tossing and getting the answer, tossing and getting the answer. That is which is denoted by x, n, and n is always greater than equal to 1. This is a sequence of random variable. Now here we also have one more thing, that each sequence, suppose x1 sequence, x2 sequence, have its own mu's or means, which are represented by mu1 mu2 up till mu1. So these are all mu's. So what does weak law of large number says? Weak law of large number says uh, uh, for that x 1 upon n, or simply let us first write it in probability. That probability modulus of 1 upon n summation I goes from 1 to n xi minus 1 upon n summation I goes from 1 to n mu i's is greater than epsilon should reach to or converge to the probability 0. This is our weak law of large numbers. Now, instead of this term, I can write it as probability modulus of x bar n, because this is the mean of xi's, and mu bar n, because this is the mean of mu i's, is greater than epsilon. This probability always converges to 0 for all epsilon is greater than 0. This is a very important concept, but this weak law of large numbers exists only and only if Bn is equals to, Bn is a variable which is nothing but variance of summation I goes from 1 to n xi upon n square. It exists. If this situation exists, if Bn exists, then only we can conclude that that random variable xn follows weak law of large numbers and always converges to the probability in probability to 0. Here it is in probability always. I have told you weak is because it is giving us convergence in probability. If it would have been giving us the convergence in almost surely, then this would have been strong law of large number that we'll be doing after this topic. But today it is about weak law of large number. So I hope the concept is clear how the weak law of large number came and why do we have to find this. Okay. Now exist also mean that it is less than infinity. Okay, I hope that this weak law of large number concept is clear with all of you. Now moving forward to some of the properties of weak law of large numbers. If we say properties of weak law of large numbers, then the first property is its sufficient property. Sufficient property says that whenever Bn, which is nothing but variance of, or we can directly write Bn upon n square. You can correct this term here. I had beforehand written upon n square. It is not upon n square. Bn is equals to variance of summation of xi's. So if Bn upon n square reaches to 0 as n reaches to infinity, this is our sufficient condition or sufficient property, you can say, of weak law of large numbers. Okay, that Bn upon n square always reaches in probability, converges in probability to 0 as n reaches to infinity. Now the second theorem is necessary and sufficient condition. The necessary and sufficient condition for this would be, for weak law of large numbers would be, let us suppose that we are talking about Sn. Sn is nothing but the summation of all the xi's, x1, x2 up till xn's. These are the summation of Sn. Now if we have to find the necessary condition, necessary and sufficient condition, then expectation of Sn square, okay, expectation of Sn square upon 1 plus Sn square reaches to 0 as and when n reaches to infinity. This is our both necessary and sufficient condition for our weak law of large numbers. Now here let me make some changes. This is suppose yn and Sn is yn minus expectation of yn upon n. Then this condition follows. This is not the sum. It is actually the formula that I have given, no? Yn minus expectation of yn upon n. Now the third and the most important property of this weak law of large number thing is our Kingin's theorem. What does Kingin's theorem says? Kingin's theorem says that if xn 1 upon n summation I goes from 1 to n, xi in probability converges to expectation of xi. Similar to this, if we talk about 1 upon n summation I goes from 1 to n, xi also converges in probability to expectation of xi square. Okay, this is our Kingin's theorem, which states that if this converges to x is expectation of xi, and this converges to expectation of xi square. This is xi square here. I hope that this theorem is clear. These were the properties about weak law of large number, and weak law of large number is one of the most important topics according to your exam point of view. So I hope that I have Made you understand it well. Now let us move to question number 1. Let xn be a sequence of random variables and mu and bn be their expectations. Then variance vn is equals to variance of x1, x2, xn. So they have given us variance. Now here also this vn represents nothing but bn. I have told you bn is nothing but variance of summation of xi, which also can be written as variance of x1 plus x2 up till xn, right? Here they have denoted it by vn, so we will also take vn instead of bn. The condition vn upon n square reaches to 0 as n reaches to infinity. Vn upon n square converges to 0 as n reaches to infinity. This one is which condition? This is sufficient but not necessary condition. Option number B. Both necessary and sufficient condition was are that here you can see this is just a sufficient condition, not necessary. And if you have to calculate about necessary and sufficient condition, then it is expectation of x square upon 1 plus s square reaches to 0 as n reaches to infinity. So this is our answer. If you know the concepts, you'll be able to solve it within no time. Now let us see this question. Here they have given us that x1, x2 up till xn be IID random variables with the mu and variance. So they have given us expectation of x is equals to mu and variance of x is equals to sigma square. And they have given us that we have to find x1 square plus x2 square up till xn square upon n in probability reaches to c. Then what is the value of this c? Now from this concept only, let us see that this x1 square plus x2 square up till xn square can be written as 1 upon n can be taken outside, and this can be written as summation I goes from 1 to n xi square in probability converges to C. Now this is Kinchin's theorem that I have told you earlier. It is nothing but expectation of xi square, right? So C is equals to expectation of xi square. Now how will we calculate expectation of xi square? This is variance of xi, this is expectation of xi. Now we know that variance of xi is equals to expectation of xi square minus expectation of xi whole square, right? So variance of xi is sigma square. Expectation of xi we have to calculate, and this will be mu square is equals to expectation of xi square. By comparing this equation and this equation, we get c is equals to expectation of xi square, which is nothing but equal to sigma square plus mu square. So we had to calculate the value of c here, which is sigma square plus mu square, option number C. This is by using Kinchin's theorem. Okay. Now moving forward to one of the similar kind of question. Here they have given us digits. So they have given us that all of the xi's follows Poisson distribution. So if xi follows Poisson distribution, the expectation of xi will be lambda, which is mean they have given equal to 2, and variance of all xi will also equal to lambda, which is 2. Then here also it is 1 upon n summation I goes from 1 to n xi square in probability will always converge to expectation of xi square. Now here variance has been given to us. Variance of xi is equals to expectation of xi square minus expectation of xi whole square, right? So variance of xi is lambda, which is 2, and expectation of xi is plus 4, 2 whole square, which is equals to expectation of xi square. And from here, expectation of xi square comes out to be 6. So this in probability will converge to our 6, which is our option number C. Okay, I hope that it is clear. Now moving forward to another question. Let us see this one. Here also, as you can see that they have given us that x1, x2, xi be a sequence of IID random variables, and with the PDF, they have given us the PDF of x. So, and they have given us xn in probability converges to C. Now we know that 1 upon n summation I goes from 1 to n xi will always in probability converges to expectation of xi, right? This is by weak law of large numbers. So we have to find the value of C they have given us, and C is nothing but expectation of xi. So we have to find expectation of xi. So here expectation of xi is nothing but, because this is a sequence of IID random variables, and from the PDF we can see that this is a continuous random variable PDF. So it will be expectation of xi will be integration x goes from theta to infinity x into e raised to the power minus x minus theta, we can take it in bracket, dx. This is our value for expectation. Now if we calculate this, let us consider in here integration. Let us consider x minus theta is equals to y, then dx is equals to dy. So replacing the terms here, we will be getting integration. Now theta will be 0 and infinite. The limits will be 0 and infinity. And in place of x, we can write y plus theta. And in place of e raised to the power minus x minus theta will be e raised to the power minus y. Dx can directly be replaced by dy. Now on solving this, this can be solved in two parts, 0 to infinity y into e raised to the power minus y dy plus 0 to infinity. Theta is a constant, it can be taken outside, e raised to the power minus y dy. Now in solving this, this first integration is a gamma distribution, is a gamma integral with the value 2. So I am directly writing it. It is gamma integral with 2. And gamma integral with 2 will be equal to 1 factorial, which is 1. This is 1 plus theta into e raised to the power minus y upon minus 1 will be 0 to infinity. When we put the limits, it will be e raised to the power 0 is 1 and e raised to the power minus infinity is 0. So it will be theta only, 1 only. So instead of writing all of them, we can write it as theta. So our expectation of xi came out to be equal to 1 plus theta from here. And hence our option number B is the correct answer for this. What is the value of C? The value of C is 1 plus theta. This was an easy one. You just have to know what kind of law or in probability. Here you cannot apply the probability because x bar n is given, and hence you need to know that weak law of large number can be directly applied instead of calculating the probability. Okay, so I hope that it is clear. Now moving forward to the last question for today's lecture. Here, this is the one. It is a bit tricky, but it is easy if you know the concepts. Okay. So here they have given us the PDF of a random variable x, and they have given us yn, in which we have to define this, and they have given us one more limit of p, and from where they have asked us the value of k. So first of all, as you can see that they have defined a random variable yn xi minus 1, and here also I am seeing x minus 1, both are same kind. So let us substitute first. So let us take as, let us consider x minus 1 is equals to u. Let us consider this. So fu will be equal to gu, fu will be equal to gx. Okay. F is taken by x, so gu is equals to fx into modulus of dx upon du. Right? This is our, yes. This is our changing of random variable portion. And when we calculate this, this came out to be 1 upon 2 e raised to the power minus u by 2. For all, here x was greater than 1, here u will be greater than 0. If we put the limits here, x minus 1, it will be 1 minus 1, so it will be 0, and 0 otherwise. This is our PDF for you. Now we have to calculate yn is equals to 1 upon n summation I goes from 1 to n xi minus 1 whole square. Now xi minus 1 is equals to u. So instead of writing xi minus 1 whole square, I can write ui whole square. Now here you can see that they have given limit n reaches to infinity, probability that modulus of yn minus k is greater than epsilon is equals to 0. They have directly given us that it converges to 0. So here this will converge to 0 when? Let us see this. So yn is nothing but, instead of yn we can write 1 upon n summation I goes from 1 to n ui square converges in probability to expectation of xi square by weak law of large numbers, as we all know. So we have to calculate expectation of xi square. So by this formula, expectation of xi square, oh okay, I have written xi square, it is ui square. Expectation of ui square. Expectation of ui square, when we keep it in here, it will be, now you can see here it follows exponential distribution. This ui from here we can say follow exponential distribution with the parameters 1 upon 2. From this PDF only you can see that this is exponential distribution with the parameter 1 upon 2. So expectation of ui square is equals to variance of ui plus expectation of ui whole square. Now variance of exponential raised to the exponential with the parameter 1 by 2 will be 2 square. 1 upon lambda square will be 2 square, which will be 4, plus expectation of ui will be equal to 2, which is lambda, 1 upon lambda, which will be equal to 2, and here 2 square will be equal to 4. So expectation of xi ui square will be equal to 8. Now this thing we can directly write here, limit n reaches to infinity, probability that modulus of yn minus 8, because it converges to 8, is greater than epsilon is equals to 0. Now comparing these two limits, we can say that the value of k here is equals to 8. So from this only we can say that our option number C, which is 8, is correct. I hope that it is clear with all of you. This was a bit tricky, but it was easier one if you know the concepts behind this. So that's all for today's lecture. I hope that you understood whatever we have done today in the class. And if not, then you can ask us in comment section or on our WhatsApp channel. only relevant doubts will be answered. All the best. Thank you.
Startup Academy presents Lakshya 2027, an exclusive batch designed only for serious ISS aspirants.